we'll pretty much go through the whole same scenario with a different type of pattern. So you've seen linear patterns. Now we're going to look at a different type of pattern. If you tried to find a common difference, you wouldn't get it. So if you subtract 20 and the 10, you'd get 10. If you subtract 10 and 5, you get 5. That's not a common difference. So this is not a linear pattern. But what I might notice is that it has a common ratio. It has everything. This is multiplied by 2, this is multiplied by 2, this is multiplied by 2. So we have a ratio that's common. In this situation, it's 2. So when you see that you have a common ratio, you know that this is a geometric, maybe sometimes called exponential as well. Not always, but so you go to your log tables, you can find the general term of a geometric. Why would I want the general term of a geometric? Same reason why I'd want it for a linear pattern. It gives me the freedom or the ease to find any part of the pattern that I want very quickly. And it tells you in your log tables that A is the first term, which in this case is 5. R is my common ratio. And you're to put R to the power of n minus 1. Can I clean that up any further? Well, BIMDAS says that you have to do your indices before you do your multiplication, so that cannot be cleaned up any further. That's your general term. Let's just check if it works. If I want my first term, then n is 1. 2 to the power of 1 minus 1 gives me 2 to the power of 0. Anything to the power of 0 is 1. That's 5 times 1, which is 5. If you want the 100 term, you throw in 100 for n, throw it into the calculator and work it out. Sometimes they might not give you the first part of the pattern. They might give you the general term. Again, this is just like a linear pattern in that they can do all the same things. It's just my pattern looks different because it has a common ratio, not a common difference. So you could create your pattern by going right T1. Anywhere I have an n, I should be putting in a 1. That gives me 6. T2. Anywhere I have an n, I'm putting in a 2. That gives me 12. T3. Anywhere I have an n, I'm putting in a 3, which gives me 24, and so on. And I can see there my common ratio, again, is being multiplied by 2. If I want to show I have a geometric, then I can just do this. But if I want to prove I have a geometric, then like we did for a linear pattern, for linear, because we know any term minus the previous one gives me the common difference, in this situation, any term divided by the previous one gives me the common ratio. So the reason that I'm using this general way of saying it is because proof requires you to generalize. So what is Tn in this situation? It's 3 to the power of 2n, sorry. And divide that by Tn minus 1. Well, anywhere I have an n, I need to throw in a minus 1. And then I'm going to try and simplify this. And I know my answer, my common ratio is 2, so I'm expecting the answer 2 here. And because I won't have put in any values for n, so no matter the value of n, I should get the answer 2, will show that it's the full sequence is geometric. My rules of indices say if I have something over something, I can subtract my powers. So that's 2 to the power of n. I'm subtracting the powers now. That's a rule of indices. That gives me 2 to the power of n minus n plus a 1. Gives me 2 to the power 1, which is 2. This sequence is geometric because no matter the value of n, when I get any term and divide it by the previous one, I got the answer 2, which is what I was expecting. So very much like what we've done so far with linear, it's just we have to think about it that it's a geometric. As with linear, we could sum up a geometric. Again, there's a formula in your log tables, so if you had 3, 6, 12 and so on, again you'll try and recognize what type of pattern it is. It's common ratio of 2. I might try and change that actually, so let's go for a different one. Let's go for 2, 6 and 18, just so we have a different common ratio. So common ratio is 3. And if they asked me, so I'm sure it's a geometric, and if they asked me to sum up the first 10 terms of this geometric, then I can go to my log tables, get my SN formula of a geometric and fill it in. A is my first term, R is my common ratio, and because we're looking for S10, I know that N is 10. If you threw that into your calculator, you'd get the sum of the first 10 terms of that geometric. So we can do all the same things. I guess good questions to do if you have the book is page 217. You can randomly pick what questions to do, but I'll pick a few trickier ones for you to do. 8 is a good one. 10 and 12 are good. And 13. And you could do 17. You don't have to do all of these. You can just pick and choose.